Okay.
Up. Yeah, welcome to our session. First talk is by Florian. And Florian, please have a screen.
Okay. Thanks, Misha, for the introduction, and thanks a lot for the invitation to speak here on this workshop. It's a pity that I couldn't come to Paris, but I hope that my message also can be understood via this Zoom type presentation. So I will talk about our recent work that we did in Stuttgart over the last couple of years on impurities in cold gases. And so what we are working on in Tillmann-Faust group is we work with Rydberg atoms that we place in ultra-cold matter. And the latest, our latest endeavors are experiments where we kind of transformed the Rydberg atom into a single ion. And then we were interested in the physics of such a single ion, a single ionic impurity, a charged impurity when you immerse it in a cold gas of atoms. So this work that I'm going to present is mainly done in two laboratories here. Two different experiments. It's two experiments that work with ultra-cold rubidium atoms. You can see the two teams here. These are our two Rydberg teams. One team has been working on a machine that allowed to produce relatively large Bose-Einstein condensates of rubidium atoms and then place single Rydberg atoms inside such a condensate. And the other team has worked on the construction of a new apparatus that features a so-called ion microscope that will allow us in the future to look on such impurity systems with very high spatial resolution and single particle resolution. So I'm going to present the results of both of these labs today. But before I do so, let me give you my short introduction to the world of impurities in cold matter. I think I can keep this relatively short as we are in an impurity workshop, so I don't have to talk too much about it. But essentially, when it comes to studies of single impurities immersed in cold gases, there are not too many different systems and platforms available. So let me summarize them a little bit. There is certainly the beautiful work by various groups, including groups in Innsbruck, in the US, and so forth, on ensembles of neutral impurities that are immersed in Bose and Fermi gases. And so those are typically probed on a kind of ensemble average, for example, using radio frequency spectroscopy. And this allowed, for example, studies of polaronic physics in these systems. One can study impurities in the context of lattice systems under a quantum gas microscope. These are examples here from the group of Arthur Videra in Kaiserslautern, or the Munich group, Emanuel Bloch's group in Munich, where essentially spin chains have been encoded in lattice systems of cold atoms to study spin impurities. So this can be done because quantum gas microscopy is available for these systems with a single particle resolution, as you can see here. And so then there is the group of ion impurities, which are different in its nature. So these are charged impurities now, not neutral impurities. And the typical approach to study such ion impurities is to combine a trapped gas of cold atoms, for example, trapped here in a dipole trap, and then merge this system with an experimental setup that hosts an ion trap. So this is a picture here, how this looks like in a typical setting. So you have an ion trap, you focus laser beams through that can also hold simultaneously a cold gas of neutral atoms, and this allows you to produce an ionic impurity. And so our Rydberg impurities are somehow, let's say, a fourth class of impurity systems where we use actually the strong Rydberg blockade that allows us to produce only a single Rydberg atom at a time from a cold gas, for example, a Bose-Einstein condensate. And so these kind of impurities are somehow a bit different in nature because I would call them a mesoscopic impurity. The reason for this is that the Rydberg atom is typically much larger than the typical interparticle distance in the system. So you can you can expect physics that occur because you have atoms that sit inside an atom. Yeah? So this makes these kind of impurities a bit different from the neutral and, for example, the bare ion impurities. And so let me talk a little bit about what kind of physics you can expect when you have a Rydberg atom that is excited from a cold gas, and in a situation where you can have other atoms, other ground state atoms from the cold gas within the Rydberg orbit. So this is illustrated here. You have the ionic core at the center, you have the electron on a high-lying Rydberg orbit, and if the density of the gas is large enough, then it's very likely that other ground state atoms can sit inside the Rydberg orbit. And that gives rise to the fascinating world of so-called ultra-long-range Rydberg molecules. So this kind of molecular bond is due to the fact that this electron here can scatter off the ground state atom, and this scattering process can lead to an attractive, essentially attractive potential between the electron and the ground state atom. And so this can lead then to a kind of system where the Rydberg atom and this ground state atom are bound together. So this is the typical potential of such a Rydberg molecule. It has actually the shape of the Rydberg electron wave function. And we have done a lot of work in this direction over the last couple of years, which I actually don't want to focus too much in this talk. So you can find a few papers that we have published here in collaboration, for example, with Peter Schmelcher's group in Hamburg, where we looked in detail on the molecular physics of these systems, for example, spin couplings in these molecules and so forth. So this alone is a very interesting topic and can be studied in great detail. But the interaction I want to talk about today is actually not so much the interaction between the Rydberg electron and the ground state atom. I want to focus on the fact that this Rydberg atom has an ion as a core. And so this ion interacts also with the grounds, with atoms that are close by, neutral atoms that are close by. And so the potential that describe this interaction is the potential of an ionic impurity now immersed in a cold gas. So the potential between a charged ion and the ground state atom is a C4 potential. It's a polarization potential. It has this type of a form. So it scales with 1 over r to the distance to the power of 4, 1 over r to the 4, and has a characteristic strength that is given by the C4 coefficient. So, and my talk today will be about this type of a potential. What can one get when one works with an impurity that interacts with such a C4 potential? So this brings me to the world of cold ion atom systems, and I would like to give you a little bit of flavor what is the experimental challenges to produce such impurity systems with a cold ion. And so this is summarized actually here in this table. What you see here is the kind of traditional approaches that immerse a Paul-trapped ion of various species into a gas of cold atoms. And what you see in this table is the typical collision energy that can be reached in these systems. So you see the typical collision energies for various combinations is in the kind of millikelvin regime, 10 to the minus 3 Kelvin. And so if you compare this now to the so-called S-wave limit of ion atom scattering, so the temperature limit that you have to reach to bring such a system into the world of bare S-wave quantum scattering regime, then you see that there is a huge gap in between what can be realized experimentally and what you have to what is the limit for S-wave scattering theoretically. This limit is actually shown here by these vertical lines. Depends very much on the species you choose, but it's typically in the range of a few microkelvin down to hundreds of nanokelvin. So the world of quantum scattering for such an ionic impurity is notoriously very hard to reach experimentally in these hybrid systems. And so the reason for this is that the temperature for these hybrid ion atom systems is typically limited when you trap the ion by the micromotion of the ion in the Paul trap. So because of the radio frequency fields in the Paul trap, the ion constantly jitters around in the Paul trap, and this leads to typically temperature scales that are in the millikelvin range. And so this makes it very, very challenging to reach this S-wave regime using such combinations of an ion trap and a co-trapped neutral gas. There are some ideas to try to approach this limit. For example, you can use very light atoms that raises this S-wave limit to higher temperatures, to tens of microkelvin. And there is actually beautiful work recently published by the group of René Geretsma in Amsterdam, who has demonstrated that it is actually possible to, even with these with the ion traps, to lower the energy of the ion by a very good micromotion compensation down to a regime where you start to see quantum scattering effects. There's another approach by Tobias Schätz in Freiburg, who aims to trap ions optically. And so this experiment actually allowed very recently for the first observation of a Feshbach resonance between an ion and cold atoms. So that was also a breakthrough in the field. There are also ion atom scattering events in molecular beam experiments, for example. For example, you can visit the work of Friedrich Merck and his team in Zurich. So our approach is to make an ion from a Rydberg atom now, and don't use a Paul trap at all, trying to keep the ion in the gas as long as possible without any trap. And then let's see how far we can get and what we can see. And we have done a bit of work by keeping the electron around, so to say, as a Faraday cage that prevents the ion from flying away by external stray fields. And so we have published a paper where we could actually see indications of ion atom interaction inside the Rydberg orbit by Rydberg spectroscopy. I don't have the time to go into the details of this paper today. Today, I want to actually really show you the work where we have removed the electron from the Rydberg atom and then played with this ion that is left over. So this brings me to the to kind of the outlook over the experimental results that I'm going to show you now. I will start with our experimental scheme to actually produce a low energy ion from a single Rydberg atom. I will show you how we do that by a specific photoionization scheme. And from that on, I'm going to show you data where we have then studied transport dynamics of such an ionic impurity in a Bose-Einstein condensate. And then finally, I want to come to this new apparatus that we have built, an ion microscope that allows us to look onto these systems with extremely high spatial and also very high temporal resolution. And so this new instrument actually allowed us, and this is really brand new data, it's not even published, fresh from the lab, allowed us to observe yet another molecular bond that is formed by an ion that is bound to another Rydberg atom. So you have an ion and a Rydberg atom, and these two objects formed a new molecule that I'm going to show you.
Excuse me, just a quick question. What do you mean by low energy ion, a low energy ion in this context?
I mean, with low energy, I mean an ion that has low kinetic energy. So the and low means
slow, right? Slow center of mass.
Slow center of mass motion.
Right. Okay.
Specifically, the ions that we produce start with a few microkelvin temperature, and then after a couple of microseconds, they heat up to millikelvin temperature. I will show you a few more details on the next slides about this. So let me start off with how do we actually produce these low energy ions from a single Rydberg atom. So the process goes as follows. We are starting off with a, let's say, dilute gas of rubidium atoms held at a few microkelvin, maybe hundreds of nanokelvin temperature. And then we excite a single atom in this gas to a Rydberg state using a photo excitation scheme. We are working with rubidium. That means we use 2 photons, one in the blue for 20 nanometer, one in the red at about 1 micrometer. That allows us to go from the 5s ground state in rubidium to Rydberg s orbitals with very high principal quantum number. Typically, our principal quantum number that we can control can go up to 200. So the fact that we only make a single Rydberg excitation is due to strong Rydberg blockade in the system. Specifically, the blockade radius here is much larger than the entire cloud. So it's just not allowed to have a second excitation in the cloud in our system. And on top of that, our excitation lasers are focused down to about a micrometer spot size, so that we exactly know where we produce this Rydberg atom. So it's an excitation that we can locally control relatively well. I see at the screen that some of, like, half of my slides are
More
black.
than a half.
More than half. Oh, that is bad. Here
Just
I can,
one fifth of your slide is visible.
did that just change, or is it?
Not okay. Blue death.
No, blue screen.
Blue screen.
No enter detected.
Huh. Okay.
You see this on the camera. So I'll show you, because it's intellectual camera, it should focus on me. So that's how you look like.
Huh. Now we are back. Okay, so you have to interrupt me when it happens again or so, yeah? Okay. Okay, so this is the way we make the Rydberg atom. And now how do we ionize this Rydberg atom is by using a specific photoionization scheme. What we do is we go from the Rydberg state. Do you see my cursor? Yeah, this is possible.
Yeah.
Okay.
What you see, we see.
Okay. So we go back from the Rydberg state to the 6p intermediate state and then into the continuum. So this is a 2-photon process. And the way that it's done is we are parking this laser here just a little bit above the continuum threshold. And so that means that when you rip off the electron by this photoionization scheme, the ion receives only a very tiny bit of kinetic energy. So it's the excess energy can actually be tuned down to a level that it's less than 10 microkelvin initially. So this process allows you to make a very cold and very slow ionic impurity in the beginning. You can even make this whole process essentially recoil-free, because these 2 wavelengths here are very close together. So there's only a very tiny bit of a recoil that the Rydberg atom picks up upon this ionization scheme. Okay, and then we have essentially a free ion that is floating around in our chamber, sits inside the cold gas, but there's no micromotion because we don't have any trap around. And now the challenge is to keep this ion cold and very long in the gas so that you can see some interesting physics. And we can do that because we have a very exquisite control of electric fields in our system. Yeah.
Just a question from ignorant person. N, you know N or not? You just.
We know N. Yeah. N is, we know N. So it's
just not necessary for us to know what is N, right?
Yeah, in this experiment it was 190, but it doesn't matter too much. It can also be 160 or so. It just has to be large enough that the entire cloud is
No. N which is shown there, NS on the diagram. I'm talking about that. Yes, this N.
Yeah, this N is on the order of 150 to 200.
Oh, okay.
So it's it's a very, very large Rydberg atom. Actually, the size of our Rydberg atom is beyond a micrometer. Yeah, that's the size of the atom that we produce here, and then we ionize it. So now, because we don't have any ion trap around, we can work with tiny electric fields that we can now point essentially in any direction we want. And this allows us now to induce a controlled transport of the ion inside the gas. Yeah? So for example, in the first experiment that we did now with this object is we applied a small electric field of just a few millivolt per centimeter, a very tiny electric field, to pull the ion to the side. And now the first physical process that we wanted to observe is what happens if you want to excite now yet another Rydberg atom in the system. So you have now this single ion. Yeah.
Florian, it's me asking. So do I understand correctly that basically here the position of your ion is just like a classical parameter, right? It's not, I mean, the position is frozen by your beam and you put it where you want.
Yes.
It's okay. It's like a pin input. Okay.
Yeah, it can be considered as a classical object, a point charge that you control.
Thank you. Thank you very much.
So in the first experiment, what we wanted to see is how well can we control the motion of this ion now. And so we have to probe it. And for now, at that time, we didn't have any ion microscope around. So one has to find a way now to probe this single impurity and where it sits in the gas. So and we did that by dragging it apart for a certain time and then trying to excite another Rydberg atom at this initial position of the ion. And so if you do so, you see a trace like this. So this is the Rydberg signal of this second excitation that you try to produce as a function of the time of flight of the ion. And so you see when the ion is initially very close to the spot where you created it, you cannot excite a second Rydberg atom at this spot. And only when the ion is far enough away, you see that the Rydberg signal emerges again. And so this type of behavior is due to the fact that such a single charge can block the excitation of a Rydberg state here. Yeah? So it's an ion-induced Rydberg blockade that we observed here. And so the physical picture for this is denoted here. So what is plotted here is the potential between this single ion and a potential Rydberg atom that you create at some distance from the ion. So it's also a C4 potential. It's a charge neutral potential, but here with a C4 coefficient that is immensely boosted compared to a ground state atom that interacts with the ion, because the Rydberg state interacts so much stronger with the electric field of the ion, because it has a much larger polarizability. So specifically, this potential can reach over a distance of tens of micrometers, can reach megahertz energies. So and if your excitation laser now has a bandwidth, or your excitation pulse has a bandwidth that is smaller than this energy at a specific distance, then this excitation is blocked. So it's a very much as the Rydberg blockade, but here induced by the presence of a single charge. And so at that time, it was possible for us to map out, for example, the blockade radius. This is shown here, the blockade radius as a function of principal quantum number of the Rydberg state. The black lines here are theory calculations that fitted very well the experimental data. And so I just want to emphasize that to do such an experiment, you have to have extremely good control over the electric fields in your experimental region, because any tiny electric field will act on the ion and will push it out of your cloud or drag it out of your cloud. So in our case, we had control over the electric field down to a microvolt per centimeter, 100 microvolts per centimeter for these experiments. Then this allows you to control the ion motion by applying millivolt per centimeter electric fields. In the next step, we wanted to use this system now to study ionic transport through a condensate. And so for this, we actually did kind of the same setting, but we increased the sample density. So we increased we evaporated more down to lower temperatures, went to a Bose-Einstein condensate of rubidium atoms, and by that, the density in the sample increases by about an order of magnitude. And if you do so, then you can expect that the ion, when you drag it now apart from its initial spot of creation, that it scatters with the atoms in the BEC frequently. And so we wanted to see this kind of scattering motion and try to understand it and measure it. This is a picture now of kind of the heart of the experiment where we did that. So what you see here is a cage of electric field plates that sits inside vacuum. And so our Bose-Einstein condensate is produced inside these plates here. And this allows us to, first of all, shield electric fields from the outside to a very good degree. And then we can apply electric fields in this chamber in essentially all directions at this level of about 100 microvolt per centimeter control. And so now if you want to, the way we studied this transport is we didn't do the trick with the second Rydberg atom that can actually probe how far the ion moves. That was a bit tedious and needs a lot of statistics. What we did is we have sent the ion to an ion detector, a microchannel plate detector, and from the time of flight of the ion to the detector, one could actually infer how fast the ion was traveling in the condensate. This was such a data set, and so we compared a situation where we had a BEC present and where the cloud was actually very dilute, and so you could see from the delay time to the detector, that's the difference here between the red and the blue data, it was the delay time to the detector. You could see if the ion was scattering on its way through the gas or not. And by such analysis of such traces, we could actually calculate back the position of the ion as a function of the time it travels through the condensate. And so this is data here for different applied electric fields. And so you can see that the ion initially has kind of a linear trend. Yeah, so its position is linearly dependent on the time it travels through the gas. And so this means that you can extract kind of a drift velocity just by fitting these linear trends here with a linear function. You can deduce a drift velocity and plot this as a function of the electric field that you apply. And so this gives you then a mobility of the ion in the BEC. Yeah? So the slope of this drift velocity as a function of the electric field gives you a drift velocity. And so we kind of compared the situation to a diffusive scattering model, to a Langevin model that accounts for each and every collision of the ion when it travels through the BEC via a Langevin event. And we found a very good agreement between a theoretical description of diffusive motion that is microscopically understood by individual Langevin collisions.
What do you mean by a good agreement? I mean, there are two linear plots here. So yeah, what sort of parameters do you use for the Langevin?
Yeah, so for the Langevin collision itself, we use the Langevin scattering rate. Yeah, and we account for the fact that our condensate is not a homogeneous, infinitely extended gas. It has a finite density distribution. That means the ion sees a higher density in the beginning, and when it kind of travels towards the end of the BEC or to the edge of the BEC, the density gets less and less. So all these finite density effects are included in the model, and then we see the result of this modeling is actually this black line here. So the black line would be the theory, and the blue line is the experiment. Now one sees that the mobility that we measure is a little bit higher than what this scattering model provides us. But what we believe is that this difference between theory and experiment can be understood by the fact that, and I don't have the time to go into the details of this, but there is another process happening, and that is three-body recombination of the ion and atoms in the BEC. And we believe that these three-body recombination events can lead to this slight discrepancy between experiment and theory. We have also tried to, or we have done a modeling that includes essentially a quantum mechanical description of the scattering, but it turns out that so far for the velocities that we probe here, such a Langevin classic kind of semi-classical Langevin description is sufficient to understand it, and there's no quantum effects yet that are expected at these energy scales that the ion has. I hope this answers your question.
Yeah. So my question essentially was how. So do you have any fitting parameters in your Langevin model, or is it just
no?
Oh, okay.
There's no free parameters.
No,
the density
okay.
is measured separately. The microscopic parameters that go into the scattering rate, which is essentially the C4 coefficient, is from atomic data. So there's no fitting parameters. A completely fit-free simulation of the experiment.
Right, and the temperature, is the temperature factor here?
The temperature of the gas is I mean, we go to a condensate, and so the condensate is,
I see. So it is excitation of particles from the condensate by collisions. I see.
Yeah. So compared to the ion, you can essentially neglect the temperature of the BEC.
Right. Okay. So there are no Einstein relations between diffusion coefficient and mobility in this context, right?
No. Yeah.
Okay. Very good. Okay. Thank you.
Okay. Okay. So this brings me now, and I have like about 20 minutes left, I guess. This brings me to this new apparatus now. So these have been kind of the first experiments that we did with this newly created single ion without any trap. Yeah? So this ion-induced Rydberg blockade and these transport measurements. So parallel to this experiment, we have set up a completely new apparatus that allows us now, that is now running, it's now completely online, allows us to observe these kind of systems, these systems of single ions and single Rydberg atoms with extremely high spatial and also temporal resolution. And let me guide you through this new system, what it is. So this is a quantum gas microscope, but not an optical microscope, it's an ion microscope. And this new device allows us now to essentially image Rydberg atoms or ions by sending those ions from the region where we do the physics, so the region where we produce the cold gas and where we produce the impurities, by sending this ion now through a stack of electrostatic lenses to a spatially resolving ion detector. And these electrostatic lenses are designed in a way that the resolution of this instrument down here in the experimental region is actually better than 200 nanometers. So you have 200 nanometer spatial resolution, and this MCP here is intrinsically a device that has also a very high temporal resolution. So that means that you can, in principle, observe processes on the time scale of 100 nanoseconds or even less. And that's kind of the dead time of the detector. So it's an instrument with extreme high spatial and very high temporal resolution, allows you to probe dynamic processes. It allows us now to make these free cold ions, untrapped ions, under such a microscope and observe these type of physics now with this new detector. I should mention that similar apparatuses have also been built in Tübingen by the Vortag group, by Georg Reitel very early on, and also by Herwig Ott in Kaiserslautern.
These microscopes, should they work for only charged things, or it doesn't matter much? I mean,
it doesn't matter as long as you can transfer the neutral atoms into charges. So the detector works for charges. The whole ion optics certainly works for charges. But as long as you can ionize your neutral atoms, it can also work for neutral atoms. Yeah?
lens is true optical lens. It's not a kind of electric field, which.
No, it's electric field. It's
yeah. So
lenses.
already at level lens, they should be charged. Kind
yes.
of.
Yeah. Yeah. So you have your sample here. You ionize your atoms, then you send them through the lens and bring them to the detector. I can show you how this looks in real life. Yeah? So this is now pictures of the various elements, how they are assembled. So all the quantum gas production happens down here in our science chamber. It's a steel chamber. Typical procedure is that you have a Zeeman slower, you cool down the atoms into a magneto-optical trap, and then we have a transport into this science chamber. And then on top of this chamber, which is already like this big, we have a tower which is 1.5 meters tall. And so this is the ion microscope. It's a very long object because ions have a large mass compared to electrons. So compared to an electron microscope, the ion lenses have to work much harder, so to say. And so this makes this instrument quite long. So it has, as I said, it has a stack. It's a stack of 3 electrostatic lenses. One sits directly on top of the cloud, and there is a second one here and a third one here, and then a drift tube to the detector. And so these lenses can be seen here in more detail. This is kind of this is the first ion lens. This is the second ion lens. That's the third ion lens, and this is the spatially resolving charge particle detector that sits on top of the instrument. And just to give you an idea, to produce all these parts here, this has to be done with very high precision to get rid of all mechanical misalignment of these lenses. So this is all work. I mean, you have to produce these parts here with kind of micrometer precision, and that was kind of a piece of art by our mechanics workshop that was able to do so. Then if you have that, the nice thing with an ion microscope is you can actually, just by setting voltages, you can, so to say, configure the device. You can set, for example, the voltage on one of these ion lenses and change the magnification of the device from let's say 100 or so to 1500. Yeah? So just by changing voltages on the ion lenses, you can tune the magnification of the ion microscope, which is, if you want to do that with an optical device, you have to change lenses and move lenses around. Here you just play with voltages on the device. We then tested this new setup using an optical lattice that actually so we loaded atoms in such an optical lattice, and then we ionized the atoms and then projected them onto the charged particle detector. So what you see here is a picture of a one-dimensional optical lattice, a standing wave with a period of 532 nanometers, not imaged optically, but imaged with the ion microscope. And
curiosity, what is the size of detector?
Pardon me?
Size of charged particle detector. Just, you know, if you talk so much about this device, it's now curious, what is the size of detector?
So between 5 and 10 centimeters, roughly.
Oh, so that's why, wow.
Yeah. So it's a rather big device. Yeah?
So no, because I'm just counting, magnification is factor of 1000. So like initially you had, if you initially had 1 millimeter, then it's 1 meter. So if you have 100 micron, right? So then it's your detector. I see.
Yeah. So it's a centimeter range, this detector. Yeah? And so you also see that you have like okay, the field of view can even be better, but you have a rather large field of view of such a device where it makes a kind of.
I'm terribly sorry.
Yeah.
It is. I think this is a very important place, because this is where you say, you are able to read this image, of course, but when you say you can see the image of a one-dimensional cloud here, I honestly don't know what you are talking about. It's some round thing with stripes in the middle. Yeah. So yeah. So how do I read this image?
Yeah. So what this picture shows is, what we have is a retro-reflected laser beam. So it's an optical lattice which is made of one standing wave. So it's a stack of pancakes. So in this image here, you look, so to say, from top onto this stack of pancakes. So each line here is essentially a pancake, yeah? But you just look on top of this pancake.
Yeah,
So,
from the side.
from the side.
Yeah.
Okay,
Yeah.
great. Yeah, that
So you see it here in this little sketch. So the pancakes are oriented like this, yeah, and then you look like this little eye here is looking from top, so to say. This is supposed to be the detector.
Very good. And is the round thing? Is it round because that's the field of view, or is it round because the pancakes have different diameter?
No, it's round because this is the size of the detector finally.
Okay, so that's the field of view. Okay.
Yeah, that's the field of view.
And the 1D tubes are horizontal, right? So you look from the side on them.
No, we look from top.
Because I see a little cartoon in the top left corner of you. So
yeah. So
yeah. So tubes are like horizontal things. Where are these? So your eye is on top.
Yeah. Yeah. So the detector sits on top of the machine and looks from top. Yeah.
So microscope enlarges. I see. And the tubes are vertical.
So it's not tubes, it's pancakes. Yeah, but the pancakes are vertical. Yeah.
Pancakes. So it's basically you're talking about 2Ds so far stuff,
Yeah.
not 1D. I see.
Yeah.
I see.
Yeah.
I see.
So maybe let me mention one more thing. So first of all, this kind of measurement allowed us to infer the resolution of the.
I also have a question. Can I stop you for another question? Do you detect? I'm sorry. Do you detect all of your atoms there, or just a fraction? So what I see there, I guess each point is an atom, right? Where it should correspond.
But it's many shots. So this is one thing that one has to mention. This ion detector can detect a few ions in each experiment. Yeah, so you cannot detect hundreds of them at a time because the ion detector has a dead time. So this image here shows, so to say, the sum of many realizations. But in each run, we ionize only a few atoms and then send them to the detector.
Okay, thank you.
The detector gets few of many ionized.
Okay, this last question I didn't get.
You ionize few, or detector gets few out of many ionized.
We ionize only a few.
So those who you ionize, detector gets.
Yeah, exactly. Okay, so from these type of pictures, we could then infer the resolution of the microscope via a detailed Fourier analysis of these patterns, and we found that the resolution is better than 200 nanometers. I would also like to mention that this is also different from an optical microscope. An ion microscope does not rely on kind of on the wave. It does not rely on the wave nature of light. So it's not a diffraction limited, so to say, device, and that means that it can have a very large depth of field. So in this picture here, you see again a picture on top of these pancakes, but now the ionization region in these pancakes was actually chosen much larger, and you can still see this structure. That means that the depth of field of the microscope is very large, and it can actually be estimated to be larger than 70 micrometers. So that means that you can shift around your sample along the optical axis of the device, and it stays a sharp picture for a very long distance. The next thing is that you can operate this ion microscope in a pulsed mode. That means you exactly know when you ionize your atoms in the sample and send it to the detector, and then from the time of flight to the detector, you get a third information, and that allows you to reconstruct even a three-dimensional image. Yeah.
I don't understand. I see here tubes, not pancakes. Sorry for so many interruptions on this cartoon.
Yeah, it's because we have different ways to make these structures. Yeah? So this is a tube, this is a pancake structure. Here we have made a structure from just an interference pattern that we projected through such a slit pattern here onto the atoms that made a three-dimensional structure. It doesn't matter if it's tubes or not. It's just a three-dimensional structure that we project onto the atoms that allows us to demonstrate that you can really make a 3D image of the cloud, so to say. So, and this is the reconstructed three-dimensional image of such an interference pattern that you illuminate on the atoms. Using this pulsed mode operation, you can do three-dimensional imaging via this additional time of flight information, and the measured vertical resolution of the instrument at that time was around 6 micrometer, but it should be possible by eliminating a few technical things to get it better than 1 micrometer, even in the third dimension. So let me come now to, can I use the last 10 minutes? Or, yeah, so it's
of
not,
course.
Okay, good. Let me come to a bit of physics that we did now with this instrument. The first experiments that we did now is we looked on the system of an ion that we produced under the microscope now, and the second Rydberg excitation that we have then placed inside the system. So you remember what I talked about in the beginning, this ion-induced Rydberg blockade. We can see this now spatially resolved. So what you see here in this picture is you make an ion in the middle, and then you make a second Rydberg excitation at a specific detuning from the bare Rydberg resonance, and this gives such rings here, around the ion. And so this is exactly the resonance condition where you, so to say, get facilitated excitation of a Rydberg atom that is seeded by this single ion in the middle. And so this picture here allows you now to kind of map exactly this potential, the C4 potential that describes the interaction of a single ion with these surrounding, with a Rydberg atom close by. Yeah. So this experiments that we did before on the Rydberg, on the ion-induced Rydberg blockade, can now be done with this great spatial resolution, so that you really see these facilitation shells of Rydberg atoms around a single ion. You can go further and even measure dynamics. So what you see here now is you have an ion, you produce a Rydberg atom close, I mean, on a certain sphere around the ion, and then you just look what happens. And what you see is that the Rydberg atom is now attracted by the ion and kind of falls down the C4 potential. So you can also see dynamics in this microscope. And last but not least, I promised you to show you a bit of very new data, so to say the very latest results from this lab, and that is the observation of a new type of molecular bond, a molecule that is formed by an ion and a Rydberg atom, and the molecular bond is kind of formed by this ion-atom interaction. So now I have to explain a little bit how this can happen, because here you see the interaction potential between an ion and a Rydberg S state, and all you see is a C4 potential. So anything that you would any Rydberg atom that would sit here at a certain distance will just see an attractive force and will be attracted towards the ion, and then something happens, maybe some chemical reaction, and that's the end of the system. But if you go away from an S state and you go to a Rydberg P state, then you can find a very interesting scenario. So what is plotted here is now the energy of Rydberg states as a function of the distance to the ion. And so when you work with a P state now, that's an example of a 54 P state, you can see that there is an avoided crossing at a certain distance from the ion between the P state and these Rydberg states here, which are states of very high angular momentum. So those are the kind of hydrogenic high L states, the states that come from that shift due to the linear Stark shift. And so in this kind of avoided crossings here, you can get potential minima in which the Rydberg atom gets, so to say, trapped. And so this is depicted here. You can get such a potential minima for the Rydberg atom. And in this minimum, you can have discrete vibrational states that then lead to a new molecular bond between an ion and a Rydberg atom. So it's an ion bound to a Rydberg atom. And the reason why you get this, potential minima is because the Rydberg atom changes its polarizability when it crosses through such a crossing. So this is how a p state would look like in the electric field of the ion. Yeah, so the electron would be more towards the ion. Yeah? And so if you then move further inwards and you turn into this high L state, then the polarizability of the Rydberg state just flips sign, and the electron would then sit on the other side of the ion. And so this gives rise to this potential minima here, the change of the polarizability as a function of distance to the ion, and gives rise to this molecular bond structure. And so with this ion microscope, we were now able to measure this new molecule by, again, creating an ion. Once it's created, we tried another Rydberg excitation close by, and then we sent the ion and the Rydberg atom to the detector, and we detected this object. Yeah? And this is the spectroscopy that we then did. So
could we ask you at this spectroscopy point? Yeah, we have a question. 50-4P. What is lifetime? This
couple of 10 microseconds, or roughly 40-50 microseconds is the lifetime of such a Rydberg state.
Why so long for dipole? For p state, could kind of.
Okay, yeah. that is the 50 microseconds, 40-50 microseconds is the blackbody limited lifetime of a Rydberg p state. So it can decay via spontaneous emission or via blackbody induced transitions. And
the question is not why longer. The question is why so long? How come? So it's like they should instantly die. No.
No. Why?
Dipole state is coupled to everything. It's like little dipole, you know. Contrary to S is, who cares? S is not symmetric function. When you have dipole so strong, it can.
Yeah, but
compared to S, it lives shorter than S state, or not?
No.
No. Okay.
Not much. I mean, maybe a numerical factor, but it's the same order of magnitude, the p state. Yeah.
Okay.
You have to be away from any Förster resonances or so, any kind of resonant processes. But if you stay away from this, then
the point of this question is that SS transition is a forbidden transition, so it's optically forbidden transition. But the PS transition is a dipole transition.
Okay. Yeah. But
so when you say that the lifetimes are comparable, that is a little puzzling.
But also, if you think about only radial transitions,
yes,
then there are also p states which are, I mean, low-lying p states. So also an S state can decay not to the ground state of the atom, but it can decay to some lower-lying p states.
Yes. So, if there are low-lying p states, yes, indeed.
Yeah.
Okay.
Там матричные элементы маленькие, там симметрия такая, по идее.
Okay.
Yeah.
So what you see here now is spectroscopy data of actually the states that live now in this potential well, and you can see that we can, via spectroscopy, we can nicely resolve all these vibrational states. So they are typically spaced by a few megahertz, and so this is the first direct observation of this new type of molecule formed by a Rydberg atom that is bound to an ion. We can also prove that this is a molecule by now using again the spatial resolution of the detector. So we can make the molecule, we can initialize, we can photo associate it, and then we can apply a little electric field and drag it. Yeah? And what we see is that if you just drag an ion for a certain time and then look on the system with our spatial resolution, you can see that the ion travels a certain distance. Yeah? Let's say here it's roughly 20 micrometer or so. If you make a molecule, it travels about half the distance because it has twice the mass. Yeah? So you can even see this on the detector now, that the object that you create here is a bound object with two atoms that just travel halfway. So the last thing that I want to mention is you can not only see the center of mass motion of the molecule, the resolution of our detector allows us also to observe the spatial structure of the molecule itself. Yeah? Because this is an extended object that is typically on the order of a few micrometer in size. So the spatial resolution of our detector allows us now to look at the spatial structure of the molecule. And what you see here, or let me show you this slide. What you see here is now, if you make these molecules and you have the ion in the center, where do you excite the Rydberg atom, or where do you get the Rydberg atom as a function of various polarization settings of the excitation lasers? Yeah? And so you can see that depending on how you polarize your excitation lasers, you can either get a situation where you excite the Rydberg atom, so to say, at the north or at the south pole, or you get something that is more isotropic. And so we have also simulated this by a model that includes the whole transition probability from the ground state to this molecular state, taking into account all the Clebsch-Gordan coefficients and so forth. And it all fits very well, but it shows you the capability of this instrument now to observe this new molecular bond with spatial resolution. I think this gives all a very interesting outlook now for future experiments. I have shown you that we can make single low energy ions with low kinetic energy in our apparatus. We can, for example, study transport through a condensate, and this new ion microscope even allows us to do all that with extremely good spatial resolution. Now, the next things that what we want to investigate under this ion microscope is we want to kind of do these transport experiments also with this fascinating imaging capabilities. And our holy grail, so to say, is to reach the quantum regime of ion atom scattering. So this is really what we aim for. We want to see that we can bring this hybrid system of ion and atoms down to a regime where quantum scattering effects dominate. And then one can think about new forms of ionic, of charged polarons. One can even play in principle with the bath, change it from a bosonic to a fermionic bath. And so these are all very exciting things that we want to investigate in the future. And with this, I thank you very much for your attention. And I'm happy to answer your questions.
Yeah, not out of politeness, but from my heart, thanks for wonderful talk, really. Like from the bottom, how to say, from the bottom of my heart, right? Yeah, okay, from the bottom of my heart. I don't know why this expression, maybe from top of my heart, but anyway, so questions.
Yes. I have a question. So with your detector, I mean, when your ion travels through the BEC, there should be like three-body recombination, right? Ion, atom, atom. And do you detect these products like ion plus atom in some state on your detector?
Yes, so we see this happening. So in about 1/3 of all realizations, we see that the ion undergoes a chemical reaction during the way through its BEC. And the way we see this is actually that we don't detect an ion what we then detect on the detector is a molecular ion. So the
Okay.
3-body recombination as a product results in a rubidium 2+ molecular ion and a neutral atom.
And how do you know this? Because you know time of flight.
Yeah.
Your lens is also works for double mass.
Yes.
I
Yeah.
see. So
Yeah.
you have a control over that.
Yeah.
Okay. Good. Great. Okay. Thanks.
Other questions? I have just yeah, for the future naive questions. When you mentioned about polar and all other that physics, so this will be kind of a charged particle, but another type, and so ions will be also charged. What will be the interaction? So it will be the same kind of charge. So like. Because the interaction is very strong, but they are both charged. So when they are different, they will interact weakly relative to this typical kind of repulse or whatever.
Okay, so the interaction that you get is the C4 potential, yeah?
Yeah.
And so the typical...
On top of the charged cloud, how the question is how you will kind of see this on top of the kind of would this particle be neutral? That's okay, but you have this kind of Rydberg, which typically, if you wish, there's a charged particles. So I mean,
so maybe to be clear, when I talk about our ideas that we want to use this device to study charged polarons,
yeah,
then it's without a Rydberg atom. Yeah, so it's only an ion. Okay.
Okay.
And so if you bring in another Rydberg state,
yeah,
then this gives rise to many more different phenomena that I tried to show you. For example, this Rydberg, this ion-induced Rydberg blockade, or this new type of molecular
exactly.
bond.
Yeah.
But just to be clear, what I mean here by an ionic polaron is only the ion, no Rydberg. Okay.
Okay. Yeah, I see.
Yeah.
Any other questions? Okay, if not, then again, thanks for wonderful talk. Florian, could you please send me the PDF file? We will add it to the conference site if you're not against like you have unpublished things, but you're okay with if we put on the site, right?
Yes, yeah.
Just a warning, you know.
Yeah. Okay.
Okay, so then I stop recording. We thank Florian.
Thanks a lot.
Thanks you a lot for coming. Так.